Hello, class. Okay, so mentioned before, there are four fundamental equations that govern the subject of classical electromagnetism. These are basically like Newton's laws are for mechanics. And we've covered two of them so far, Gauss's law and Ampere's law. And I want to talk about Gauss's law for magnetism. So if you remember Gauss's law in electricity, we have the flux is equal to the charge enclosed divided by epsilon naught. So we have to have some closed surface here. And so like the electric flux defined, we're going to integrate over our surface. So generally what we'd have to do is break this up into pieces. So like for any given piece here, we have this vector dA, which is pointing outwards. We can always say it's pointing outwards in Gauss's law because we have a closed surface that has an inside and an outside. So then we take, the dot product of the electric field with that dA vector, where that vector is perpendicular to the surface in that small region. And then we just integrate over the entire surface. And so we define magnetic flux the same way. So to distinguish them, although we usually don't really need to, it's usually obvious from the context if we're talking about electric or magnetic flux. But for magnetic flux, we would define it the exact same way. Just using magnetic fields instead of electric fields. And I'm just going to tell you what Gauss's law is. And Gauss's law for magnetism is that the flux through any closed surface is zero. And so this is a very different thing than we had with electrical charges. So I mentioned before, if you have, say, a bar magnet, historically we call them the north and south pole because the north pole of this magnet will point to the geometric north pole, or the geographic north pole of the Earth. And so historically we call these poles, but they function just like charges, except they're magnetic. But what's different about them, say we take this magnet and break it in half. So you might expect something like this. One end has a north pole, the other end has a south pole. And so we break it in half, and we might expect this. We have a south pole here and a north pole here, but that's not what happens. Turns out each of the pieces has a north and a south pole. And as far as we know for sure, we can keep breaking this magnet into pieces, smaller and smaller, and this is always going to be that case. And that's really what Gauss's law for magnetism is telling us. So like say we had a north pole by itself. This is called a magnetic monopole. Remember, they act just like electric charges. So remember what the magnetic fields for a bar magnet? If you consider just a positive and negative charge, we'd have a dipole, and the fields look just like each other. So this looks just like an electric dipole. And so if we say we draw a Gaussian surface around this, okay, let's try that again. So we draw a Gaussian surface, and if this was a magnetic monopole, the same rules would apply for electric charges. The electric field lines would start on positive or north charges, and they could only end on a south pole. And so here we would have a flux through this surface. And so this Gauss's law for magnetism says that this can never happen. Now, it is believed that magnetic monopoles exist, although there's no evidence for it. There are theoretical reasons, but in the subject of classical electromagnetism, there are no magnetic monopoles. Who knows? Maybe there aren't any. And so that's what Gauss's law says for magnetism. Now, I'm wondering, like, how does this bar magnet? This is the thing we're most familiar with before studying physics, anyways. Well, when you think of magnets you can stick on the refrigerator or things like this. How does that tie into what we've been talking about? And we talked about the source of magnetic fields. Say that magnetic fields come from moving charges or currents. We have Ampere's law, or the Biot-Savart law, that tells us that currents create charges. And that is true. That's where, currents create magnetic fields. That is where they actually come from. And so we have to talk about how something like this is a result of electric currents. And like I said, we can break down this magnet as much as we want into smaller and smaller pieces. Each one is going to have a north and a south pole. And you might ask, like, is there some point where you have to stop and you just have an isolated pole? No, you can go all the way down to the subatomic level. So let's look at an atom, for instance. We have a nucleus, which has protons and neutrons. And again, this is a somewhat primitive model for an atom, but the nucleus, and we have electrons. And the electrons, this planetary model, they orbit the atom. And that is a current. This electron is a current. It's a moving charge. And so it should create a magnetic field. Now, an electron, say, going counterclockwise, let's draw this from a different perspective. Say this is the nucleus of the atom, and this is the orbit of the electron. Say the electron is orbiting this way. That would be a current going in the opposite direction. So the current would be going this way because electrons are negative charges. And so the magnetic moment, or the magnetic moment for a loop, which is what this orbit is, this is a vector. I'm just going to write down the magnitude. So in this case, we just have one loop. It's one electron orbiting. And so n is 1. But the current times the area, which if we assume a circular orbit, is pi r squared. Now, I should point out that this planetary model was extremely successfully initially at explaining some things that were not understood before. But then it kind of had some difficulties trying to go into more detail. And so they actually considered just like planetary orbits. These electron orbits are elliptical. And, but yeah, ultimately this idea had to break down and be replaced by quantum mechanics. But anyways, this orbiting electron creates a magnetic field. And matter is made out of atoms that have, like every atom has electrons circling. So in a sense, it's not terribly surprising that magnetic fields can exist in matter. Like this magnet is made out of atoms with circling electric charges. Each one acts like a little magnet. There's more to an atom than this, though. One is the electron itself. It has it creates this magnetic field because it's in orbit, just like a circular current creates a magnetic field. But what if we just had an isolated electron that's not orbiting an atom? Turns out this has a magnetic field with it as well. Electrons have a property called spin. And again, you can think of an electron as, say, a little ball of negative charge, and say it's spinning on its axis. That would kind of be a current as well. And so electrons have an intrinsic magnetic moment associated with them as well. And what about protons? They do as well, but they're much smaller. The intrinsic magnetic moment of a proton is a lot smaller. And also, it's not orbiting. So it's usually disregarded. If you look at an atom, the magnetic moment ultimately depends on both the spin and the orbit of the electrons. And so again, it's not terribly surprising that we can get magnetic fields from ordinary matter. I guess what might be a little surprising is why don't normal objects, like this marker, does not create a magnetic field around it, even though it's made of electrons. And there's various reasons for that. One thing is that electrons like to pair up with each other in ways that cancel each other out. And so if you have a neutral atom that's like an even number on the periodic table, they tend to just cancel each other out. And also, you can ultimately look at an individual atom as having a magnetic moment. So let's say you have one atom that has a magnetic moment like that. But if you have a large collection of atoms, if they're not arranged in any particular way, if they're randomly oriented, then the overall effects are going to cancel out. Yeah, there has to be some kind of reason for materials to have an overall magnetic field associated with it. And there's three types of magnetism in matter that I want to talk about. One is called paramagnetism. So let's say we have some matter here. And this object is not magnetic. So it could be anything. Oh, almost anything. And let's say we apply an external magnetic field. Now, in a paramagnetic material, that would cause if you picture each atom as being randomly oriented, if you have a magnetic moment in a magnetic field, there's going to be a torque on it that's going to try to line them up. So before this magnetic field existed, if these atoms have a significant magnetic moment associated with them, and the reason it's not a magnetic material overall, there's no measurable magnetic properties associated with it, that's because they're randomly oriented. But if you apply an external field, they're going to line up. And so the net effect is we're going to create this internal field in the same direction as the external field. And so now we have a stronger magnetic field inside and maybe a little bit outside this material as well. And typically you'd expect odd numbers on the periodic table to be paramagnetic, because electrons like to join together in ways that cancel each other out. So if you have, say, 26 electrons, you have 13 going one way, 13 the other way, they cancel out. But if you have 27 electrons, that one isn't going to be able to pair up. And so every atom is going to have this one electron that's creating this magnetic moment. But overall, no noticeable effect because of the randomness. But now yeah, now we line them up, and we have this internal field that lines up with the external field. And that's where the term paramagnetism comes from, parallel. Okay, now not every material is paramagnetic, but typically odd numbers on the periodic table. Now there's another phenomenon that all materials have, and that's called diamagnetism. And so before you have this material with no magnetic properties, you apply an external field, and it's going to create an internal field that opposes the external field. So you can think of the term diametrically opposed. That means opposite direction. So that's called diamagnetism. All materials have this property. It ultimately comes down to quantum mechanics to really explain why materials have this. Later on, I can give you an incorrect explanation, but but I don't know if it's worth giving this incorrect explanation because it is wrong. But anyways, this is common. All materials behave this way, including paramagnetic materials. But in a paramagnetic material, paramagnetism wins. So you have this diamagnetic effect, but you also have this paramagnetic effect, and that one is much stronger. Okay, now one thing that both of those paramagnetic materials and diamagnetic materials, something they both have in common, is that if you remove this external field, they go back to just being unmagnetized. So that internal field only exists when the external field does as well. There's one more type of magnetism I want to talk about. It's called ferromagnetism. Okay, well, ferro, or like a ferrous metal, it's like iron. Now, if you look at this on a microscopic level, I actually have a picture. I didn't bring it with me, but I'll do that in class. I'll hold it up to the camera. But you can actually see this with the right kind of picture. Not visually, but with x-rays, you can actually see this. What happens in a ferromagnetic material, so I remember atoms typically in most materials, just the magnetic moments are kind of randomly arranged. And a ferromagnetic material forms these regions called domains, where in every domain, the atoms are lined up. So like in this domain, all the magnetic fields line up this way. In this domain, that way. And they're all kind of randomly oriented. And so typically the net effect is zero. Like if you just have iron, this might be going on inside, but because there are so many domains and they're all oriented randomly, iron typically does not have any, it does not create a magnetic field. So they all cancel each other out just by randomness. But it's interesting when we create an external magnetic field. Let's say we create a weak external field, maybe nothing's going to happen, but then we start increasing the field. Eventually one of these domains is going to kind of spontaneously flip, where it's like all the atoms line up almost at once. And then another one's going to do so. And eventually it'll reach what's called saturation, where all of the domains are lined up. And so like in every domain, it's like they kind of all spontaneously flip. I mean, obviously it can't be instantaneously, but nearly so. And so now we create a very strong internal field. So if you have iron and you apply an external field, you can get all these domains to line up. And so it kind of looks like paramagnetism now, except maybe the details are different. Paramagnetism is much quicker. You apply an external field, atoms just line up with it. Here they have to kind of reach a point where they all flip at once, so it'll probably occur a little bit more slowly. But otherwise, it seems like, other than the detail of how this internal field arises, it might seem the same, but there's a very critical difference between ferromagnetism and paramagnetism, and that is that if we remove this external field, the domains stay as they were. And so now we have what's called a permanent magnet, because they're going to stay this way, and this is how a magnet is created. So you will now have a permanent magnet. Permanent might not be the right word to use here, because it depends on these domains being lined up, and they will tend to stay that way, at least for a very, very long time. However, you can scramble this back up. One way to do it would be to heat this, because, heat, you add thermal energy, the molecules move around, so you could destroy this nice kind of alignment that you have with heat, or, so maybe permanent isn't the right way to describe it, but, close enough. For practical purposes, they will remain this way for quite a while, unless you do something to destroy the magnet. And that's one way to do it, is just apply it to a very strong field, because you want to make sure it's saturated where all of these domains line up with the external field. And again, there's a lot more we could talk about. I actually took a class once on magnetic materials, and literally the entire class was on nothing but magnetic materials. All sorts of details, like how do these domains flip over, but we're going to keep it kind of simple here. And so basically, magnetic fields ultimately come from moving charges. And atoms, you can picture an atom as like a tiny magnet, most of the time. Some atoms are very bad magnets, like helium and neon. Others, typically odd numbers on the periodic table, are much better. But on a large scale, they arrange themselves randomly most of the time. And magnetic. But, if you apply an external field, that can lead to some interesting effects inside the material. Just like electric fields. We talked about dielectrics, and they can actually weaken the electric field inside the material. Here you can either strengthen the magnetic field or weaken it. Like paramagnetism and ferromagnetism would strengthen it. Diamagnetism would weaken it. Okay, so I think that'll be all for this one.